Hello, my name is Alex. So my talk is not going to be about any particular product. It's going to be about state of the art in science right now. It's kind of a prelude to get towards describing a paper that won the Best Paper Award at this year's Computer Vision conference. And I find it really incredible. Some of the interesting achievements, and I wanted to share them with you because this is, as you know, PyTorch Meetup. And everybody here probably knows PyTorch, right? How many of you trained your model using PyTorch? That's a lot. That's great. That's what we want to see. Because I'm kind of not trying to describe something that is going to be useful tomorrow. But I'm thinking it shows you what direction the area is going. Because AI, I've been working, this is going to be the plan for today. I wanted to talk briefly about me. I spent 15 years in machine learning and AI, and it was kind of an aspirational field for me, because I guess a lot of people thought that it's going to be a transformative thing. In the past 3 years, kind of situation a little bit changed now. It's more real, grounded, we have it. We can do LLM agents, but I still think there's a lot of areas that can be expanded, and there's a lot of space which can be improved. So yeah, I worked on that. I did my PhD on 3D deep learning, founded a couple of startups, some successful, and I strongly believe that artificial intelligence is something a little bit more complicated than just language models. Because obviously, ability to operate in reality requires interacting with reality, not just language artifacts. It's if you read 50 billion books, it doesn't matter, you're not connected to reality. So you got to act in some way. And to do that, you need some form of perception. So I wanted to describe briefly the problem, the 3D reconstruction problem. It's an area, maybe can be considered computer vision, where if we have a lot of images, because we probably know that in the past recent couple of decades, there have been an explosion of photography technology. Everybody of you have a smartphone, which is actually mostly camera now. It's actually, amount of tech there is incredible. And the quality of the data that is gathered inspired Mark Zuckerberg to actually rename the company at some point. But those images can be useful for something, not just recognizing particular object, but reconstructing the whole world. And this area is called 3D reconstruction, or sometimes might be known as photogrammetry, a science of creating something more complicated. Because as you can see here, reality is more complex than any image, because image loses a lot of information. You see only things from one perspective. So there's several subtasks in this area. One of them is structure from motion. If you have a sequence of photos, and the video is essentially a sequence of photos, but just in a really quick succession, you need to be able to determine where those pictures were taken from. So this is first part of this kind of 3D reconstruction process is we're taking those images and we position each picture where it was taken in 3D space, and we know where we're looking at, which direction. So don't be scared. No, it's not a complicated math. But in the most simple incarnation, it's just it's geometry, and equations. It's just figuring out equations and if you have a 2D picture, you have x, y. If you have a 3D thing, you have x, y, z. So you need to find a way to compute the z from a bunch of x, y's. And this is some linear algebra, but we're not going to get into that right now. Essentially, the more projections you have, the easier it gets, because you have more equations, and if you know, the more equations you have and less variables, the easier to solve, essentially. The second step is when you know where the pictures are taken from, you can proceed to a second step, which is computing point cloud or any kind of 3D representation of the thing we're looking at. So essentially, the reality and computer is modeled often as a mesh, a bunch of points, 3D points in space, or sometimes voxels, like in Minecraft. And one of the big achievements in that area was the paper Building Rome in a Day. Called that because it, I guess, Rome wasn't built, but like the 3D model was built in a day. Essentially, they mined a bunch of images from Colosseum, and they were able to reconstruct it just like running the algorithms. And those pictures probably been taken by tourists over like some period of time. So this is kind of what was a showcase. And it uses an algorithm called bundle adjustment. It's essentially an optimization problem. When you have a bunch of points in space and you need to find, like, solve those equations, remember? And when you have a lot of them, you can solve it in a way to minimize an error. Like in machine learning, most of the time in machine learning, what we do is minimizing error of some sort in training and finding a solution. Because like machine learning is just like a different way of programming computers, giving the constraints and asking to find a solution. Pretty much always. This space, we're going to find like the 3D points. Doesn't matter. It's optimization. And then we start to think, like, looks classical. This can be done probably without PyTorch, without deep learning. Why do we need it? Well, there's actually been an explosion of, like, for the past maybe like 10 years, of approaches of solving like those reconstruction problems using neural networks. And there's too many of them to describe. It's like there's no point in it going it. But essentially, understanding that reconstructing reality, you need more data. But if you don't have data, you can use some other data to use what we call a prior. Essentially, make a model, make a computer know what a shape of things is, right? But not specifically the shape of like this chair or this chair, but like in totality, you know? And I think it can be argued that it's kind of like a 3D spatial reasoning as well. When you have a partial observation and you're trying to generalize. But this is much more grounded. It might be considered generative AI in some form, but it's much more grounded because we are constrained by the data that we got from, well, the first step when we like take pictures. Yeah, there's a bunch of them, and you probably heard this word. Transformers is the architecture that underpins a lot of language modeling and actually other problems as well. So you're familiar with language models when the text is modeled as a sequence of tokens. And those tokens have like a lot of dependencies between them, right? It have grammatical structure. It might be like, oh, you're asking like, find me an answer about this document. And then it's kind of like going through a billion sequence of your inputs and like, oh, this is the answer. So that can be kind of applied to a lot of wider range of algorithms and models. So 3D space, like looking at images, we can do that in sequence as well. I'm trying to like explain that deep learning used to work like the models, you show it a picture and it always gives you one kind of answer, and it spends the same amount of computation on it. Transformers, in more general sense, they allow you to sequentially look at long sequences with complexity inside them and reason about them in a sequential manner and give answers in a sequential manner. It's not reasoning, whatever they're saying, like language model can reason. No, it's not. But it's something close to it, you know, like finding a needle in a haystack is pretty impressive. But it's also not just about like finding, it's also about constructing a new thing. Transformers were built for, like the original paper was about translation task, about taking a sequence in one language, translating it into another language. And it's actually can be applied to a really wide range of areas. Because like you gotta fill in the gaps in a language sequence. It's like, oh, I don't know this word, but like in a translation, you gotta make a decision like how to translate it. So it kind of uses a prior. So 3D thing can be considered in a similar way. You're looking at a sequence, you're filling out the gaps, something that you don't know from your internal prior, and you're creating a new representation of this thing. So this can be leveraged. Transformers for 3D. There was a paper last year named Duster. We're not going to go super deep into the detailed architecture. On the next slide, maybe. Essentially, it looks at pair of images, and it's able to output the 3D reconstruction, partial 3D reconstruction of what the thing is into images. But the kicker is, if, like in a classical sense, you have two pictures looking at the same object, there's this condition, right? You need to look at the same object to connect the same dots. This thing was able to generalize when pictures are almost not overlapping. So imagine I'm taking a picture of this part and taking a picture of this part. And then it will be able to tell me that it's part of the same room using a lot of like internal guesswork because it knows like the tubes, air vents, columns, architectural kind of like things, because nothing around us is random. This was designed by somebody with like a strong kind of architectural kind of inductive bias. The columns should be like equally spaced. There's got to be probably like exits, fire exits, whatever. So this information can be leveraged inside the model. And this is, I think, kind of can be qualified as a foundational model where you're kind of trying to capture knowledge of a certain area, not just regarding like a small subset, but in general, and be able to give answers in a general kind of situations. Yeah, so its architecture, like the clicker isn't working. Okay, so it's PyTorch Meetup again. This is our neural architecture of neural model. It takes two pictures. It turns them into small patches. Those patches are converted into tokens. And you can treat them pretty much the same way the language is treated. You know, it's like a sequence of things which correspond to another sequence somewhere. And it can be used to fill in the gaps. Then they are encoded. Then they are transformed through a transformer. Then they have like some information connection, like sharing information between the heads. And then it's outputted into a point cloud of certain shape, like, depth map, not a point cloud. And then you can use the bundle adjustment thing that we talked about before, using those depth maps, and make a more concrete reconstruction. And this is like, had some interesting results because, yeah, this is the way you kind of like leverage that. Yeah, and this is just like to illustrate how the images are turned into tokens. It's a fairly kind of, I mean, it's like it was developed in 2021, which is by AI standards, ancient history. Weird. And I wanted to conclude to like the main piece of this presentation is VGGT. VGGT. The latest architecture, which actually reduces much more constraints. It's actually, let's just abandon everything and turn it into one big transformer. And I'm kind of like, I don't know, like not disappointed, but it's a little bit, you know, the bitter lesson of like, oh, just bigger model, more data, make it like, it's kind of like, it's still working. But it's like, we spend so much time like trying to construct it in a way, so it's like, we looking smart, not the model. So this one takes like arbitrary sequence of images. Not just two, it might take one, it might take 5, it might take 200 images in a sequence. And it outputs 3D representation for each image. And then it's like you don't need to run a special additional bundle adjustment step to reconstruct it into the 3D point cloud. It can do it itself because it's just that good model. So essentially, we take a sequence of images, we convert them into patches, they are converted into tokens, then the camera token is added. This is the way of like injecting variables. You know, like whenever like you see a transformer model and they're like, this token, this token, this token, it means it's, oh, we're just adding variables that we want to be separate. Because like, oh, each image has a different camera variable. But like when it's going to be processed by global attention and all of the frame attention, it's going to be mixed in together. And then all of the information from different parts will affect each other. You know, this is what you want. You want like a picture 1 and picture 25. Oh, it's like the same part of this chair. So it's like inside of the architecture, it kind of does a lot of localization and connecting and assigning. This is what transformer models are good for. They're good at finding like connections between parts of the input. And this is worked great here. Yeah. What can it do? It can give you like camera parameters, knows where the camera is located in this for each of this sequence of images, depth maps, point cloud, and also be able to track the points in a moving sequence as well. So It's pretty nifty. It can also generate a novel view. So if like you have an incomplete reconstruction and like, oh, I want to look from this side, it can actually give you a really good guess of what is going to be there. So this is a really interesting thing of like allowing you to quantify like the things that you cannot see right now. It's really important for robotics because like always in robotics, like an autonomous driving, you have always incomplete information. You cannot have like all the cameras everywhere, absolutely. And because of that, you need to quantify like where you need to look next, such things. It's also able to reconstruct from not overlapping images, which is also great, and it shows that it's able to capture things that are not in the image, but like can connect them. So this is, I think, very impressive. You know, imagine like somebody taking a picture of you like from like, I don't know, a corner of your head, and then like, oh, this is their full face, you know? So yeah, it might be scary, but I don't think so, because it's a little bit better approach than just absolutely guessing. It's like, you can take a lot of information and put it in. Yeah, and you can also actually feed it like images and like paintings, and it also tries to do like kind of go into a painting and understand what is like 3D concepts inside an image that is, well, wasn't a photograph, which is fun. Oh, they also run it like on a Coliseum. I guess it's just a very popular thing to reconstruct. Yeah, and you've probably seen some of those images before, somewhere on YouTube, like when people say, hold on to your papers. It's, yeah, just like a demonstration of how it's able to reconstruct environments with limited data. It's actually, for some reason, if you're running a transformer, it might be even more efficient than just doing it like pairs of images. Because like when you do it in a sequence, you kind of like reusing information as you go along. And here's like time like of computations. I think it's quadratic, but GPU VRAM is scaling linearly. So if you have like, I don't know, like you have 40, 90, 24 gigs, you can do like, I don't know, 100 images. This is really impressive, you know. It also saves time and computation because all of those optimization tasks are very intensive. But here we only like train it once, and then we use it, and it kind of does the computation inside of itself. You probably heard of the thing called world models. Like, aren't they 3D foundational models? And I would say no, because they do not handle anything 3D related explicitly. They are only kind of like a rendering engines. You know, you can like press forward, you can press backwards, and what you see is like a probabilistic reconstruction. But there's no concept of a 3D space inside of it, so it cannot be used like by systems that require 3D to operate. But I mean, like for people, it might be entertaining to use it in a way. Yeah, it's a really impressive thing, but I would argue it's not a 3D foundational model. And there's a really interesting survey about like the concept, what are the world models, what they mean. Partially, it's a marketing term, I think. But yeah, if you want to look closer to it, like I have a link. There's also a thing, people trying to build robots and like do it absolutely without 3D. Essentially, like let's give a robot ability to act in a space, but like we don't care if it's like doing 3D or not. We're just gonna give it cameras, we're gonna talk to it, and we're gonna have like vision, language, action kind of loop, which you tell a robot like, oh, do this, do that, and it's kind of like, it will figure out 3D by itself. Like, I'm not certain that you can kind of like create a lot of safety when you're doing that because, well, I don't know, language models do not seem to be reliable for a lot of things, and I think a lot of robotics applications are more critical. You know, it's like medical settings, like, I mean, like if somebody misplaces your order from Greg's, like using like robot, it's not a big deal, but like in maybe like working with expensive materials and people might be dangerous. Yeah. So conclusion. There's a long history of computing stuff trying to recreate 3D environments using images. We have more images now than ever, like everybody. You know, I think we need to, like, if we wanted people to stop posting images, we need to pay them, you know? This is a really nice thing in your industry when the data that somebody generates for you is like essentially free, right? Because like in a lot of domains, you cannot get like 5 trillion billion pictures. Deep learning methods allow to improve that in a lot of ways. Transformers, like as the most recent kind of system to do that, also allows to do that. And a lot of application, like the same reasoning applies to it, like scaling laws of foundational models gonna get better the more data you put in. And this is, I would argue, a more concrete industrial application of like deep learning would be right now. Thank you for your time. If you'd like to talk more about it, I'm not currently researching in that space, but I'm open to projects, and I'm looking for opportunities as well, because I want to come back into that field. I think like it's going to be, well, very beneficial in the near future. Thank you.